Hello, everyone. This is Jikir Gadasara from MongoDB. I'm one of the principal solution architect here at MongoDB. And today's topic, we will discuss how to implement caching solution on MongoDB. So what is an in-memory cache? So if you Google it, the definition is basically an in-memory cache is a data storage layer that sits between your application and your core database. And the reason you need that layer is because your database is not able to meet the high speed requirements you have for certain use cases. And you're taking a portion of your data from the database and you're caching it into in-memory cache so that application have the lower latency reads and writes against that cache instead of going directly to the database. So when you look at some of the core requirements for a caching solution, the primary requirement, which is most obvious, is low latency fast reads. So we are expecting the performance and throughput so that each reads are probably like a single digit milliseconds to service your most mission critical use cases for your business. Second is could be workload isolation. What that means is that your database is busy with serving a various different kind of workloads. Some of that could be resource intensive and that could introduce more latency to your caching requirement. So to be able to isolate that and have your transactional workload on one of the servers and have a secondary nodes on the system serve your high frequency caching like a queries, then that could be happen on a separate node, but that should all be supported as same system. So that can be done through workload isolation. Third is scale horizontally. So as you grow your business, and if you require higher throughput with same lower latency, you need to be able to scale that horizontally to hundreds and thousands of requests per second, and MongoDB can support that as well. And the last one is if you have a user base, your customers spread across the globe, and you want to provide them a consistent experience, which requires probably reading from a local copy of the data, so you can distribute data globally, and then they can do the local reads from the region. That would provide the caching, like a performance from the region they are requesting the data from, and that could easily happen within a couple of milliseconds as well. So all these different requirements to meet that on top of a traditional database, you need to stand up some sort of a caching solution with your database. So why MongoDB can be used as an in-memory cache? So let's take a look at some of the fundamentals of MongoDB. So some of the core benefits of MongoDB is first, developer experience. MongoDB is designed for making a developer's life easier. Developer is easy for developers to interact with, is easy data structure for developers to align their objects with. Second, performance and scale. MongoDB has been proven in the industry as one of the highest performing database, and it can scale horizontally, where some of the relational databases kind of fall short on scaling horizontally. Number three is a consistent, it's a database with the distributed consistency, availability, and resiliency, meaning that we always deploy MongoDB in minimum 3 node replica set, and we can increase that as we need. So for example, we spoke about the requirements for your global customers and servicing global customers. You can have a replica set, which can have a secondary servers distributed globally in the world. Number four, security. Security is the heart of MongoDB. So we have a full role-based access control. We have a state-of-the-art encryption and rest technology, which includes both the hardware level encryption as well as the field level encryption within your application using your own master key. And number five, MongoDB is designed to run anywhere, whether you're running it locally on your laptop or on a server on-prem or a container, or we have a full solution like a SaaS on MongoDB Atlas. The beauty is it has the same MongoDB binaries and same MongoDB drivers. So it doesn't matter where you run MongoDB, you're going to have the same experience of MongoDB, whether in cloud, on-prem, or on your laptop. Now, when you think about the NoSQL world, MongoDB has been a leading technology in this world, and there is nobody else that comes closer to in terms of the ranking of the database to MongoDB. And that's because of how we store the data natively with our idiomatic drivers. We can scale and distribute data across multiple servers, so there's a high resiliency, no outage, always on database. It can run anywhere. But on top of that, we are also providing all the capabilities that traditional relational databases have excelled in terms of expressive query language, be able to have the ACID transactions, the advanced indexes, and also the tooling around security management like backup, restore, monitoring, and all of that. So MongoDB has invested into some of those tooling aspects as well. So MongoDB provides best of the both world, where you can run a complex queries with a complex index requirement, but at the same time, it has all the properties of NoSQL database, which gives developers flexibility, be able to scale horizontally, and have an ability to have a database that's always on, regardless of expected or unexpected outages, such as like a network error or hardware failure, and so on. So let's deep dive into replica set and how it can help us to build a caching solution. So when we talk about replica set, if you're not familiar with MongoDB's architecture, uh, on the server side, there are minimum 3 nodes. There's always one primary server, and there are more than minimum 2 we recommend, but you can have up to like 50 secondary servers as well. When the application and the driver connects to the MongoDB replica set, it connects to the entire replica set, and the driver is aware of the state of each node that participates in the replica set. The benefit of that is highly available environment. So if the primary server goes down, one of the secondary servers will become the primary server, and then the traffic will automatically get routed to that new primary server. So that gives us the rolling fashion of maintenance. It gives you the failover to the other servers in case of a hardware failure or unexpected network failures. And you are able to build like 5 nines uptime, for example, with this replica set architecture. And we talked about workload isolation. So having this extra secondaries will also allow you to spread your workload to the secondary servers where it makes sense. So for example, you can have additional secondary servers on top of your HA topology that you can spread out rest of the world so that the application instance running in different regions in the world, they can provide the local copy of the data and can meet the requirement of like a 2 or 3 millisecond response time for your queries. Because you can imagine if your application is in UK or Asia and they have to reach out to US, I mean, you can't beat the physics. You have to pay the latency like 50 to 100 milliseconds to come across the globe. Now, with having a local copy of the data, you are transferring the latency to the one-time writes, but then all the applications can read locally once they have a copy of the data available locally in that region. So once you have that, so MongoDB allows you to give a different controls to the developers. So they can choose how they query from this topology by what we call read preference. So by default, every query goes to the primary server, and the developer has these levers where they can specify the different settings for read preference. So for example, they can say primary preferred, meaning that go to primary. If primary is not available, go to one of the secondaries. Or they can say read preference secondary. That will route all the traffic to the secondary servers, or they can say secondary preferred as the first. And if no secondary but the primary is still available, then it will go to the primary. If you don't want any of the complications, then you say just go to the nearest node based on the network latency. Then you can specify the read preference nearest, and it will go to the nearest node in the topology. On top of that, you can target a set of list node by the tag as well. So what that means is that if you have a nodes with specific tags, you can target those by the names. So for example, in this connection string, you have the MongoDB SRV record, and you have this MongoDB cluster name, and then the read preference we have nearest, but we are also specifying the tags that only read from AWS and US East first if it's available. If that's not available, then you can read from AWS US East 2, and then we're going to apply the read concern local, meaning that give me the local copy of the data that exists on that node, and don't worry about anything else. So with this, all the application traffic will first go to the AWS US East 1, and then if that node is not available, then it will go to the US East 2. So that also gives you automatic failover for your queries as well. All right, now let's talk about the WiredTiger Cache. So WiredTiger Cache is the underlying technology that MongoDB has deployed in the server side that typically you don't really see or experience directly. but WiredTiger Cache is how MongoDB reads and writes from the disk and does the memory management, providing the caching-like capabilities to your applications. WiredTiger was a company that we acquired back in, I believe, 2010, maybe. It's probably a long time, so around like version 3 of MongoDB. And once we acquired them, we were able to introduce things like ACID transactions, memory first architecture, and a lot of other tons of benefits from the engineering perspective. So how does the WiredTiger cache work? So imagine you deploy a MongoDB servers like a 3-node replica set, and on each node, you would have this architecture. So when we say node, it's basically a server that makes up of the disk, compute, and memory. So the disk is pretty much your hard drive or SSDs, whatever you have chosen. The RAM that makes up the cache, which gets divided into two components, WiredTiger cache and the file system cache. And then compute, you will have the MongoDB process that's going to be running on the system, which is a MongoDB server. So when we have the RAM, typically the WiredTiger cache will be approximately half of the total RAM, and the rest of the RAM will be used for other processes like your connection. When you have connection pooling and each connection handle is open, there's a 1 MB per connection, and then some of the aggregations and whatnot. So a lot of the other things will use file system cache. But file system cache is also used by the query processing and caching the data as well. But most of the data is then cached into WiredTiger cache. So how does it work? So when you start MongoDB server from the cold start, it has most of its data on the disk. And as the query comes in, it will get the pages from the disk. It will load it into file system cache. In a file system cache, it will remain compressed because data always stays compressed on the disk. And then from file system cache, we will uncompress and keep the raw data into WiredTiger cache. So the WiredTiger cache is where all the request from a database perspective is being served. So when you submit a query, it is going to be looked up in the WiredTiger cache using index lookup, and then it will find that document and it will return to your application and the drivers. Now, the caching perspective, when you think about the performance, so if you have WiredTiger cache big enough to host your entire data set, that means that every time you query something, it will find it in the WiredTiger cache and it will return it back to the application. This will be the most performant workload, meaning that with the fastest response time. And typically, you can achieve on the database side, this will be like a sub-millisecond response time on the database side. And if you compare end-to-end network latency, you can easily achieve like 2 or 3 millisecond latency in the same region, kind of response time, including a network latency. So it can be really fast, and typically it behaves almost like any sort of in-memory caching solution out there, right? So with this architecture, we can deploy MongoDB for read-only cache very easily. Now, just to complete the thought process, if let's say you don't have document in the cache, then it will have a page fault in the WiredTiger cache, and it will try to load that page into the file system cache. Now, file system cache is able to hold a lot more data into memory because those pages are compressed. And it will find, if it finds that in the file system cache, then it will return to the WiredTiger cache and then back to the application. This is still really, really fast. You're probably adding only 1 or 2 millisecond at maximum um, to your query processing time. So this is still very, very, very fast, almost acting like a caching response time. The last one is if you don't have data into either one of them, then it will go to the disk, find the page, and return back to the application. So your expectation should be that your application will have to pay the latency of reading from the disk, like seeking the page from the disk, and then returning back to the application. This is still really fast. We are still talking about like around like 10, 15 millisecond disk, depending on the IOPS on the disk and how fast your disks are. But it's also really fast. But compared to the actual in-memory processing, this is still like probably 10 to 20 times slower, right? Because the disk is much slower than your in-memory processing anyways, right? So as long as your total data set fits into the WiredTiger cache, or at least in the memory, then MongoDB will behave as a caching solution, because we only the page eviction only happens when we fill up the cache and there is no more room for new pages to load it. That's when we do page fault and we evict the pages. So we use the least recently used eviction algorithm, so LRU. So with that, as long as you have the big enough RAM to host all your data, MongoDB will act as a cache on every single node. So this architecture applies to every node. Okay. With this, we're gonna go through a demo. In the demo, we have real life application. So this is we are using an example of retailer because this is where we have deployed this in production. Uh, but this applies to any industry, including banking industry, where you have your customers, and when they log in through the website, you look up the customer and you load the profile into the web application, and then from there on, the customer will interacting with the different features that you provide for online banking and whatnot, right? So in this example, we have built a customer profile which is very realistic. Customer has like a names, multiple addresses, multiple maybe gift cards and multiple credit cards on the profile. So and each customer is around like a 2 kilobyte in size. And we're going to show and for application like this, a typical response time on the database side is 5 millisecond end to end, including network latency. Some of this could be like up to 3 millisecond as well, or even faster. And so we'll show you how we can achieve that. So the requirement for this particular customer was that for 95th percentile of the workload, they wanted to have 5 millisecond response time or better. They wanted to high volume reads, meaning that they wanted to be able to go, they typically see 20,000 TPS, but they wanted to be able to go up to like 40, 50,000 TPS for the peak busy season uh, uh, workloads, right? They also have user base multiple locations in North America, so they wanted to have East and West uh, database servers, which can provide local reads. The writes were kind of a batch writes to update the customer profile, so they weren't really worried about the performance of the writes. That's why MongoDB was one of the good solutions to satisfy this requirement, because MongoDB's replica set can give you the local reads by having a nodes across East Coast and West Coast. And at the same time, it can have a primary server. We can do the writes and take the hits on IOPS of writing, and then other node can service the reads uh, at the same time. They wanted very really high uptime, so they officially asked for like 4.5 9 uptime. Reason for that is this is end user customer facing, so even if you have to go through regular maintenance like version upgrades or security patches, there should not be any outage. And MongoDB's replica set again kind of provides that benefit and architecture uh, for the highly available, highly resilient application. So with that, we're gonna dive into like how we have set up our environments. So in this demo, I'm using MongoDB Atlas. For those of you who are not familiar with the Atlas, MongoDB Atlas is our SaaS solutions where you can deploy MongoDB at anywhere in the world in any cloud providers very easily, like just by clicking a few different clicks. So in this example, we have set up 5 nodes architecture across the 3 regions. We're gonna have East, West, and Central, and we're going to have also customer applications mainly. So my demo only has the East and West, but in reality, you can have application servers running in East, West, and Central. And they're submitting their queries against their local copy of the data by using a read preference, as I described earlier. So they're using a read preference local, mainly read preference nearest mainly, so that they can reach out to the nearest member for the lowest latency reads. And that automatically also gives you the simplicity in terms of the connection string, where you don't need to have a specialized connection string for different region application servers. So they kept it very straightforward connection string with the read preference nearest, and that's about it. But you can further customize that by specifying the each cloud region or your own tags to target those nodes for your query workload as well. So with that, let's take a look at the actual demo, the live demo with the application we have built. All right, so to start with our demo, we have first MongoDB Atlas cluster. This is the size of M40, meaning that it has 16 gigs of RAM and 4 CPUs. And you can see we have 5 node cluster. 2 nodes are in east, 2 are in west, and we have 1 in central. Our primary region is US East. That means that the primary server is in US East. Now, for this example, we talked about our customer database. So the use case is that when customer logs in, we will submit an API request behind the scene. That API will look up the customer by the customer ID. And we have created customers. There are 10 million customers with a predictable IDs starting from 10 million, 1 million to 10 million IDs so that we can predictively pick a random ID and submit in the query so that we are randomly selecting a customer. And that will give us a pretty good distribution across all our 10 million customers to select. And as you can see, our database under cache, there's a customers collection, 10 million documents. There is an index on customer ID to keep it simple. So we have a unique index on customer ID that we have created. And our customer document is actually fairly complex hierarchical document, which has a lot of information about customers. And you can see that the average document size is around like 1.9 kilobyte, so around 2 kilobyte document. So it's a decent sized document. And you can see total compressed size is 2.6 gig. That brings to like almost 20 gigs of uncompressed data size. So the actual data you can imagine is a 20 gigs. And the total index size is around 400 megabytes because we only have a single index on the customer ID. So what we'll be submitting is we'll be submitting a query where we look up the customer by ID. And for workload generation, we are using what we call a Locust open source tool. So this is the Locust open source framework that we have built internally. And all it allows us to have multiple number of pods as based on Kubernetes, obviously. So it allows us to spin up a multiple number of pods, the worker nodes as on the application side, and then we'll specify the connection string like as part of project configuration. And in this connection string, as I mentioned earlier, we are also using a read preference nearest, meaning that all the requests will be routed to the nearest available node. And you can see we are connecting to the database cache, and the collection name is customers. And in terms of the actual code, this is the Python-based framework. So there is a whole set of instructions on how to collect the performance of time and everything. We are measuring the time, which is end-to-end time for latency on the application side. So it's going to submit the find one request on Python on the application side, and is going to return the document back. So that will include the end-to-end latency from the application perspective, which includes the network time as well. So what we have is we have multiple threads running right now. So you can see we have 4 workers for east and 4 workers for west. So I have 2 different instances of application running, and you can see that this has been running for a while, and they're around approximately CPU is almost like 90% on most of the workers. And you can see that when you look at the actual chart here, this is where we can see the performance data. So what's happening is on our host on East Coast is running around 12,000 requests per second at the moment. So we are looking at around like 10,000 right now. And you can see that by the time we started, initially during the warm-up time, the latency was a bit higher, but then right away in a few seconds, it kind of settled down. And we are looking at on 95th percentile only 2 milliseconds, and the average response time is actually a single digit, like 1 millisecond, 1.04. So this is pretty impressive. So this is half of the workload. The other half is running on the West Coast. So here you can see we have consistently like 10,000 requests per second, and we are also running on 95th percentile 2 milliseconds, and the average response time is just 1.06 milliseconds. Again, this is not the database side latency. This is actually end-to-end latency on the application side that application sees, which includes the network payload back and forth as well. Now, when you look at the MongoDB Atlas, MongoDB Atlas has a comprehensive monitoring feature built into it in the UI as well. So let's take a look at the real-time metrics first. Real-time metrics mostly shows the traffic on the primary server. So you can see that on a primary server, our CPU consumption is only 28%, and 7,000 of those requests are being submitted on the primary server. And you can see there is no queuing as well. And you can see on the server side latency is actually less than a millisecond because we don't even see a single like one or two execution times. This is 0 and below. So it's really fast on the server side to look up that single customer for each request. We also have a detailed metrics on every server. So what you can see here is the primary server, which is our US East, is running approximately around like 7,000 requests per second. Then we have a second server on the primary region, which is also like taking around 4,000 to 4,400, actually around 4,000 requests per second. Then we have a West Coast instance of application where it's taking one of the servers taking like 6.5 thousands to around 7-ish, 6.5 probably approximately. Other one is taking like 4.6 thousand requests. So total makes up to like almost close to like 20,000 requests per second. And you can see that all the resource consumption side by side as well. So here you can see on average, we are only consuming 20% CPU, meaning that we can probably push this even more, all the way up to like probably 40,000 requests per second without any problem. The execution time has been really quiet for the reads. So reads are below 0 milliseconds, as you can see the blue icon there. It doesn't even show up on the charts, so the reads are really fast. The cache has been really quiet. There's not much activity happening in the cache. There will be some cache loading happening, so some of the documents will be loaded in the cache. So you can see that cache usage is equally distributed across all nodes as well. It's around like 3 gigabytes that will probably make up to like 12 to 14 gigabytes of total data set size as well. IOPS are not really been consumed much as well, but you can see the workload right now is constantly hovering around 1 millisecond on average response time to 95th percentile 2 millisecond, and it's quite stable. So that's the important part. It's is really stable and is able to also do like local reads and able to sustain like 20,000 TPS per second. We can even push this further to like almost 20,000 requests per second. As you can see, there's a lot more room available on the server side. So that's our demo. I hope that kind of helps you understand how MongoDB can support the caching use cases using nothing special in terms of the settings or knobs on MongoDB server side. There was no optimization done. Everything is out of the box, default settings here. The only thing we tweaked was routing the traffic with the read preference to make sure that it goes to the nearest server in the replica set. But other than that, there was no other optimization was done. So I hope that kind of helps you understand the MongoDB's memory first architecture. If you have any other questions, feel free to reach out to me directly. I'm always available to answer your questions and even support your testing. If you have your use cases, if you would like to take it for a test run, I'm more than happy to support those kind of POCs as well. Have a good day, everyone.